All right, section 6.4 is sampling distributions and estimators. There's going to be a lot of writing and definitions and terminologies in this section. What it's doing is it's laying the foundation for what's coming up in the next section, which is the central limit theorem. If I say something that doesn't make sense in this section, I really need you to stop me because this is kind of critical foundational work. So we're going to start with a definition of the sampling distribution of a statistic, such as the sample mean or a sample proportion. That is the distribution of all the values of the statistic when all possible samples of the same size n are taken from the same population. Sampling distribution of a statistic is typically represented as a probability distribution in the format of a table, probability histogram, or a formula. So we're not talking about looking at an individual item anymore and the probability of randomly selecting a male that's too tall to fit in a doorway like we did in the last problem in the previous section. We're now talking about a sample of size, say, 10. What's the probability of randomly selecting a sample of size 10 and having the average male of a group of 10 males not be able to fit through the doorway? The sampling distribution of a sample mean is the distribution of all possible sample means with all samples having the same sample size n taken from the same population. The first time I read this, I was like, this doesn't make any sense to me until I looked at this graphic. This graphic here started making things make sense to me when we were talking about a sampling distribution. This first picture right here represents the average number you get when you roll one die. Let's start with a simulation of 10,000 tosses of a die. A histogram gives the following results when we just roll one die. And we see what looks like a uniform distribution. Now this made sense to me because when you roll a die, each side has the same chance of coming up, doesn't it? If it's a fair die. So we expect to get a uniform distribution so that this represents the number of ones we got, the number of 2s, 3s, 4s, 5s, and 6s when we roll only one die. On this one, we look at the average of rolling 2 die. What this means is we roll 2 dice. Let's say we roll a 5 and a 2. If we roll a 5 and a 2, the average of those two numbers is going to be 3.5. If we roll a 6 and a 1, the average of those numbers is 3.5. If we roll 2 4s, the average is 4. So the only way to get a 1 when you roll 2 dice at a time is to get 2 1s. The only way to get a 6 when you roll 2 dice for an average of the face values is to roll 2 6s. So when we roll 2 dice, we see that this mean here starts peaking. It's no longer what we got when we rolled a single dice, but we're looking at the average when we rolled 2 dice. It's still possible to get a 1 by rolling snake eyes on 10,000 tosses, but you're not going to get as many as you did with the ones when you were rolling only one die. So you see this peak start happening. When we increase the number of dice to 3, now the only way to get a 1 is to roll 3 1s. The only way to get a 6 is to roll 3 6s. But if I average the 3 dice together, the faces of the die that comes up, my average is going to be somewhere closer to the middle here. And we see this normality start taking shape when we roll 3 dice. Well, what happens if we roll 5 dice? You ever play Yahtzee? Yahtzee is 5 of a kind. It's hard to get, isn't it? Well, the only way to get a 1 is to roll 5 1s. The only way to get a 6 is to roll 5 6s. Yahtzees don't come up all that often. If we're taking the average of all the numbers that show up on all 5 dice, the average value is going to be somewhere here in the middle. If we increase the number of dice to 20, now there's almost no chance of getting 21s on a single roll of the dice. So what's happening to this distribution here, as you increase the sample size, this 20 here represents the sample size. Here, that was your n equals 5. So this is the distribution of what's happening when you take 5 dice into consideration. 20 dice, 3 dice this way, n would be equal to 3. And here, n equals 2. And here, your sample size is equal to 1. We get a uniform distribution if we're only rolling 1 die and keeping track of the numbers that come up. Here, we're rolling 2 dice. But notice the middle of this value here is about right in here. Here it's a little easier to spot the middle. It looks like it's about right here. Here, the middle of our distribution looks to be about right here. Here, the middle of our distribution looks to be about right there. And the middle of our distribution here looks to be about right there. Those means on all of those distributions looks to be about 3.5. It doesn't matter if I roll 1 dice, 2 dice, 3, 4, 5, 20. That mean value doesn't change when I'm looking at the average of the face values. That would be a sampling distribution for the sample mean, where n is equal to your sample size. The sampling mean is the same as the population mean whenever you're looking at samples of groups of things. Now look at what happens to the spread. As our sample size gets larger, doesn't the spread get smaller and smaller? And you can really see it here. Our spread when our sample size increased up to 20, remember the spread is how far away your data values are from the mean. That starts getting smaller and smaller. So it looks like the mean is going to stay the same no matter what the sample size is, but the standard deviation is going to get smaller. And that's going to be a key factor to the central limit theorem that we do in the next section. So I just kind of want to remind you this. The mean here for our sample distribution is going to be the same as the population. This would be our sample distribution for the x bars. But our standard deviation is going to be the same as the standard deviation of the population divided by the square root of n, if a few conditions are satisfied, and we'll get into those in the next section. I'm just pointing this out right now. As your sample size gets larger, the standard deviation gets smaller. Well, what happens when you divide a number by a bigger and bigger number? This whole thing gets smaller and smaller. So the sample means tend to target the value of the population mean. It wasn't dead on exact, but it was close. It was about 3.5 each time. That is, the mean of the sample means is the population mean. The expected value of the sample mean is equal to the population mean. The distribution of the sample means tends to be a normal distribution. Even if we took a distribution that was not normal to begin with, as we increased our sample size, we got this shape that was more and more normal. The sampling distribution of the variance is the distribution of sample variances, with all samples having the same sample size taken from the same population. So what that means is we could do the same thing here with the variances. I didn't copy those pictures. They're in your book. If all you have is my math lab, you can look at the ebook, and it's right at the beginning of section 6.4. And now this is the distribution of the sample variances, not the standard deviations. The distributions of the sample variances tend to target the population, but they're going to be skewed right, I believe, because somewhere in here it says that. The distribution of the sample variances tends to be a distribution that's skewed right. While it's similar, it's not as robust or as unbiased an estimator as the mean is. So the sampling distribution of the proportion, though, instead of looking at an average, we can look at a percent of something. For example, let's say that I'm trying to find the percentage of people that have had DUIs. So I look at a population of size n and I pull out, let's say, 100. Well, if I look at the sample proportion for all groups of 100 people, then that proportion would be just like the one for the mean. The sample proportion would target the population proportion. In order to tell the difference between a population proportion, we're going to put a hat over the sample. With the means, we use a subscript mu sub x bar for our sample means, but with the proportions, we use a p and a p hat. The sample proportions target the value of the population proportion. That is, the mean of the sample proportions is the population proportion. Now, I did use the word biased and unbiased. Unbiased estimators are things like the means, the variances, and the proportions. That is, they target the population parameter, and these statistics are better in estimating the population parameter. And the last part of this course is going to be all about estimating or inferring what's going on with the population just by looking at a sample. What we were doing in the first half of the course was describing things using descriptive statistics, and probabilities. Now we're going to be looking at predicting or inferring things about a population based on samples. Biased estimators, as opposed to unbiased estimators, do not target the population parameter. Hence, they're called biased. Unbiased is good. Biased is bad. Note that the bias with the standard deviation is relatively small in large samples, so you could use the standard deviation as an estimate. You'll hear me talk about, and you'll read in the book, talking about sampling with replacement. If you remember back on the last test that we just took on probabilities, when we had a small sample and we sampled without replacement, it changed the probability of things happening. So if we sample with replacement, then we can use the same probabilities. So when selecting a relatively small sample from a large population, it makes no significant difference whether we sample with or without replacement. But sampling with replacement results in independent events that are unaffected by previous outcomes. This makes the calculations and formulas and stuff easier. We want independence. Independent is a good thing. It makes calculating probabilities easier. And this wraps up 6.4. 6.4 is just laying the groundwork for what's coming up in 6.5.